directly in the chemical steps. Right? Is that distinction clear in terms of how magnesium could be used? When you go on to study RNA next term, and there's these big, large folded RNA molecules that can actually function as enzymes, you can imagine that the whole molecule is nothing but, has a phosphate group at every nucleotide. And for that thing to fold up into 3 dimensions in any kind of globular way that can catalyze a reaction, there's going to be magnesium decorated in that structure all over the place. And also in their active sites. So sorting out, what does a magnesium do? Is it a binding magnesium or is it an actual catalytic magnesium? You need to throw it in there for the reaction, but what's it doing? Is it just compensating the charge on the phosphate in a happy way? Well, then you could think, well, I'll just add in some sodium instead. That should be good enough. Maybe more sodium. Right? But usually that doesn't work as well. Okay. Hexokinase was also our example of induced FIT. Right? Once the glucose triggers the conformational change of the enzyme to form a closed active site, then water cannot get in, so water does not compete with glucose for attack on ATP. Right? All right, so that's hexokinase. Now, the next step, which is this one, is an example of an internal rearrangement. So this is kind of going back to those classes of enzymes, enzyme reactions that we talked about. We talked about a group transfer kind of reaction already. And we mentioned redox reactions, but we didn't talk about internal rearrangements or carbon-carbon bond formation reactions. Right? So all 4 of those reactions are part of glycolysis, and somewhere along the 10 steps. So one way to categorize glycolysis is just to kind of go through the steps and say, okay, number 1, hexokinase, group transfer. What's the group? Phosphoryl group. Right? It's the nucleophile, this, right? What's the product? Okay, got it. Next one is a rearrangement. Because I got to go from glucose 6-phosphate to fructose 6-phosphate. Is that a redox reaction? Well, you could say that this carbon here going to 2 oxygens after the reaction, it's only going to 1. So that one's reduced. So maybe this is a redox reaction, except that this carbon here, which goes to 1 oxygen before, is now going to 2, carbon 2. Right? So that guy's oxidized. So there's no net change in the redox state of the molecule. You can't say that fructose 6-phosphate is more or less oxidized or reduced than glucose 6-phosphate. You could only say that certain carbon centers have been oxidized and reduced, but they're compensating. Right? So this is not a redox reaction. Right? You could think about this reaction as elimination of water in the same way. This also gets put in this general category here. We'll see later on in glycolysis at step 8, there's a mutase that just kind of moves a phosphate group from one position on a sugar to the next. That's also a rearrangement. Right, this is a rearrangement. Okay. So it's not surprising, perhaps, that the standard state free energy, now note that all the delta G's in these slides have prime 0 on them, so they're all standard state. So none of this is relevant to the actual concentrations in the cell. Right? So don't be misled by some of these numbers. They look like, we'll get to how these numbers looks like it's impossible for the pathway to go forward because it's large and positive. But that's just the standard state. Right? By virtue of the regulation and the maintenance of metabolites, the substrates and the products of that for that enzyme, the Q factor, right? And delta G equals delta G0 plus RTL and Q. That Q depends on the relative concentrations. Right? And so regulation in the cell will control those levels. Okay. So that's the second step, and that's the sort of idea of the second step. This is a mechanism for the second step, and I want to show some of this a little bit differently by drawing it out. But basically, what has to happen on this enzyme is the cyclic form is opened up to the linear form, and then the chemistry occurs on the linear form, right? And then it goes back to the cyclic form. The cyclic sugar does predominate in solution, but the enzyme works on the linear form. Sometimes it's hard to tell how much catalysis the enzyme is really providing to help linearize the sugar. In the case of this particular enzyme, it's known that there's a histidine on the enzyme that assists this process here. Okay. And then we have this sort of central part of the mechanism, which goes through a cis-ene-diol intermediate. Okay. And I will, let's take a look at that a little bit more, a little bit better. So if we look at glucose cyclization, or linearization, right? And so this is probably something you saw last term, but the 5 position here, right? This is going to attack the C1. So this is on the same glucose molecule, right? In the cyclic form, or sorry, in the linear form. Okay. So this would be C1, which has a carbonyl H, and then this is going to go to C2. Right? So in the enzyme, in phosphohexose isomerase, this proton is removed by the action of a histidine as a general base. Right. This is not a detail that's important, but you should know. You should know that sometimes these sugar enzymes facilitate the opening and closing of the ring. Okay. So from here, it goes to this kind of configuration here, minus C2. Right. So now we've got a tetrahedral carbon form. And in the next step, this proton that came off on the histidine is donated back in, right, to form this guy. Okay, so this is cyclic. Okay, sorry, that's what I'm missing. Okay, so it's basically take a proton and then replace it. And if you have a general acid, if you have a general base on the enzyme, that can also function to redonate it to general acid-base catalysis, just like the histidine and chymotrypsin. Okay. So that would be the cyclization part of the overall mechanism. And as far as the actual mechanism, that functions by way of a glue on the enzyme. Okay. And so the glue functions as a base to abstract a hydrogen, a proton, from the C2 carbon. Okay. So it's glucose 6-phosphate now, so I'll just write G6P for the rest of it. So that's going to that. Okay. So we're abstracting this proton here, which is a very difficult reaction, by the way, right? Because breaking a carbon-hydrogen bond is tough. It's almost as hard as breaking a carbon-carbon bond. Okay. So the enzyme has to bring a lot of catalytic power to bear on here. Right? So this is the Ene-dialate here. This will go to this compound. So we've got, what do we got here? So we have the glue abstracting this proton, right, to form this intermediate here, which resolves to protonate again here, right? So that we have this compound. So I should draw in a proton there. Okay. And this proton solvent. And then from here, this is going to go, because this glue here picked up a proton, so OH. So this proton here on the glue can add to this double bond here. So this glue first functioned to remove a proton, general base, then redelivers the proton here. Okay. So here we have a base picking off that proton. Okay. So this also forms BH, and then this forms B plus, H plus. Right. And so at the end here, we release a proton that we had picked up from solvent, so there's a proton balance in the overall reaction. Okay. And the glue is redelivered into its negative charge state, which is where it started. Right? So in terms of these mechanisms, I don't expect that you should be able to write out the mechanisms from scratch. Right? The only one that I expect that for is chymotrypsin. So for mechanisms like this, I would give a lot of clues about it, and